is an old subject in maths, but has been recently applied to the study of condensed matter and has been kind of radically changing the way in which we think about electrons in condensed matter, especially leading to predictions of new quantum phases and associated physical measurements. And thanks to the work of Maia and people, her collaborators, there's now computational schemes to identify interesting topological phases and catalogs of materials that help us to search for topological systems with desirable properties. So this is the field in which I'm speaking about. I'm going to be speaking specifically about magnetism and topological electrons, and I'll give you a kind of introduction to that field and also give you some real-world examples of magnetic materials where the magnetism, the specific details of the magnetic order affects the type of electronic topology that you find and how you can control that. So I've got a message here. I'm going to just answer. Yes. Right. I'll get this to advance. Some message.
What is the message?
Just use that.
Yeah, it's working.
My fix. Yeah, so I shall speak about these materials here, which are all different real-world compounds that exhibit different types of magnetic order, which couples to the electronic topology, and I shall explain how the magnetic order couples. So just to set the scene, topology is to do with properties of systems which remain invariant when you continuously deform one shape into another. And if you go onto Wikipedia, you can see all these interesting examples of topological transitions, actually between the same systems which are topologically equivalent. And one of the reasons why this field is interesting from a practical point of view is that as we know from experience, if you try to convert one system into something which is topologically different, it's often quite difficult to do that. For example, if you want to convert a simple strip of paper into a Möbius strip, you have to actually physically break the paper, put the twist in it, glue it back together again. So what that means is that if you put a topological defect into a host, and the topological defect has got a different topology to the host, then that defect can be especially stable and robust. And this, of course, is of interest for practical applications. And in addition, the interface between the two materials, the two topologically distinct materials, can have interesting, something dramatic can often happen on the interface, which is of interest. So this is what we mean by topological protection. And the importance of this field was actually recognized in 2016 by the award of the Physics Prize, Nobel Prize, to these three British-born physicists, Thouless, Haldane, and Kosterlitz, who actually recognized that systems which are topologically distinct, systems of electrons that are topologically distinct, have a kind of order, but not a conventional sort of order like we think of ferromagnetism or something which involves symmetry breaking. This is another type of order which can be categorized by quantum numbers, special topological quantum numbers that they introduced. And this was their citation for theoretical discoveries of topological phase transitions and topological phase of matter. Some Nobel Prizes are easy to explain to the general public than others, and people had no idea what this meant. In fact, The Guardian, which is a national newspaper in the United Kingdom, tried to explain this in a simple way by saying that in the world of topology, changing from a normal conductor to a superconductor might be equivalent to changing a bagel into a bun. And still nobody had no idea what this was all about. So it is actually a difficult field to explain to non-experts. The sort of the introduction of topology into electronic crystals was really started by these theoretical papers in 2005, 2006, building on the work of Haldane, Kosterlitz, and Thouless. And they had this idea, which I'm going to explain now, which led to what's known as topological insulators. So the idea is very easy to understand. If you start with a free atom, which has quantized energy levels, so these just represent the energy of two orbitals in the free atom. You put them in a solid, in a crystalline solid, the energy levels spread out into bands like this. So this is a bit like a semiconductor where you have a valence band and a conduction band. And if the coupling is strong enough, then these bands can overlap. Now, usually what happens is when bands cross like this is you get some hybridization, for example, due to spin-orbit coupling. And so you open a gap and then you end up with an insulator like that. But what's interesting and important here is that the bands here are in the inverted order compared to the original orbitals. They're in the opposite way around. And so if you put the system in a crystal, this is a crystal, you can see that inside the crystal, the bands have this order, red below blue, and outside they have the opposite order. So the question then is, what happens when you move from inside the crystal through the surface to outside the crystal? And what must happen, of course, is that these bands must reverse somewhere, and they're going to cross over somewhere near the surface, which is where the periodicity of the crystal is removed. So what that means is it's absolutely inevitable that at the surface of the crystal, you get this twisting of the bands, and you'll get a zero gap state here, which will therefore be conducting. And it turns out that for reasons which I'll come to in a minute, these conducting states in these types of systems are very special in that they are spin polarized. In other words, a current that's going clockwise around the outside of this material will have, say, a spin up, and a current going anti-clockwise will have a spin down. And this is very interesting from a point of view of applications, because it means that if you are moving, say, in the clockwise direction, there's no process where you can scatter in the reverse direction without reversing the spin of the electron. And that makes these currents very, very stable. It makes conductivity very, very, very high. So these are very useful practically. Yeah, so I like to, so somebody had the idea that this is a bit like a chocolate bar wrapped in metal foil. So it's insulating on the inside, and it has these surface conducting states. So if you want to think about that topological, if that helps you think about a topological insulator, that's great. It's also the case sometimes that bands can cross, but without opening up a gap. So it could be that this crossing point here is protected by some kind of symmetry. And in that case, you can get features like this in the electronic band structure, where you have linearly dispersing bands away from a point. And of course, the material which exhibits this better than any, I would say, is graphene, which, as most of you will probably be aware, has these crossing points at the K points around the Brillouin zone boundary. So looking exactly like this. And there is actually a tiny gap in graphene, but it's only a few micro electron volts. And what's interesting about these points is that the electronic wave function is actually twisting as it goes through these points. And if you take a kind of walk in momentum space around a closed circuit around this Dirac point, then the electronic wave function changes its phase such that when you've been through a whole circuit around this point here, it has a phase change of pi. And this special phase change is called the Berry phase. And the Berry phase is responsible for all sorts of interesting physical and observable phenomena of topological materials. And the other thing that's interesting about this kind of band feature is that because the electronic dispersion is linear, the electrons are sort of mimicking ultra-relativistic particles. In the case where these bands are doubly degenerate, which is what you get when you have a crystal which has got spatial inversion symmetry and time reversal symmetry, then this structure, this electronic dispersion, can be described by the famous Dirac equation for relativistic electrons. And so we call the excitations around here would be described as Dirac fermions. And if the chemical potential is exactly at this point here, then this type of material is called a Dirac semimetal. Semimetal is just a material where the valence band and the conduction band are just touching at one point. So that's a Dirac semimetal. It's also possible if you break spatial inversion symmetry and or time reversal symmetry, is that you can split the degeneracy of these bands into two, so that you end up with two Dirac cones, but which correspond to the crossing of singly degenerate bands. And this type of structure, the electrons in this type of structure here are described by another version of the Dirac equation called the Weyl equation. And the Weyl equation is interesting because the electronic excitations have got a coupling between the spin of the electron and the momentum of the electron. So that's why it is that in that previous picture of the topological insulator, the surface conduction states have got well-defined spin direction. So again, if the chemical potential lies exactly at this point here, we have what's known as a Weyl semimetal. If the chemical potential is a little bit away from that point, say up here or down here, it's still possible that the material will exhibit some of the interesting physics associated with Weyl semimetals, because as long as you're on the linear part of the curve, the electrons will preserve some of the characteristics. So that's the sort of material that we get in the real world usually. And the first examples of Dirac semimetals and Weyl semimetals were discovered 2014 and 2015. You can see here, this very nicely shows the Dirac dispersion. This is ARPES data, angle resolved photoemission spectroscopy, where they've doped the chemical potential to be just above the Weyl point, the Dirac point, which is here. So you can see the Dirac cone very nicely in that material. And this is the first example of a Weyl semimetal, where you can see the two split off Weyl cones, which are caused by the breaking of inversion symmetry in this particular structure. This is also angle resolved photoemission data. So this is what you can see in three-dimensional materials. And I want to start talking about some real materials by looking at this family of compound. These are called the Zintal phases, ytterbium, manganese, and then either antimony or bismuth. And what's interesting about these materials, as I will show, is that the specific type of magnetic order has a huge difference to the sort of the topology of the electron bands. So in these materials, manganese is magnetic, carries a magnetic moment. In fact, in a sort of ideal atomic picture, it would have a spin of 5/2. Ytterbium is actually non-magnetic in this system, and the chalcogenide here is also non-magnetic. So this is the magnetic element. And until quite recently, the magnetic order in this material was not known, with the structure that the manganese magnetic moments adopt below, actually around about room temperature, was not known, and there was a few suggestions. And there was some theoretical predictions based on ab initio calculations. And so one group, for example, this group here, suggested that the magnetic structure looked like this, where each spin is in the opposite direction to its nearest neighbor, both within these layers and also along this direction here. This is called a G-type antiferromagnet. And they calculated the band structure, and what they found from the band structure was this is what's known as a Dirac nodal line semimetal. In other words, you have these Dirac cones, but the node here actually forms a line in momentum space. So that's what you get from this type of magnetic structure. Another group, this group, actually suggested that instead the nearest neighbors in the plane were opposite, but the nearest neighbors in this direction, the spins were actually parallel. And if you do the calculation for that type of magnetic structure, you get a Dirac semimetal, but with a gap here. So very different from this. And if you turn the spins in the C direction, the vertical direction, with the same structure, this is called a C-type antiferromagnet with the spins along the C-axis, you get the same type of electron band feature. If you tilt the structure very slightly so that there's a net ferromagnetic moment in the plane, you split these into two, and they overlap, and you can get two Weyl nodes like this. So I'm showing you this because it illustrates that depending upon the precise details of the magnetic structure, you can get very different features in the band structure. So how do we measure which of these is the correct band structure? So what the sort of the simplest way to do it is to do a neutron diffraction experiment where you simply diffract neutrons from the magnetic periodicity that you get. And this is an experiment that we did a few years ago. This is actually on ytterbium, manganese, antimony too. So it's one of those compounds. And this plot here shows the intensity of one of these magnetic diffraction peaks as a function of temperature disappearing at the magnetic ordering transition, which in this material is 345 Kelvin here. This is, you can think of this as an order parameter of the magnetism. And if you want to decide which of these structures is correct, what you do is you measure lots and lots of these magnetic Bragg peaks, and then you fit a model. Well, you fit each of these models to the data, and you find out which fits the best. And so these are just three of those structures fitted, plotting the observed intensity on this axis and the calculated intensity on this axis. And in an ideal world, they should all fit along a straight line with a gradient of 1. You can see that this is the best fit, and the blue and the red symbols correspond to magnetic Bragg peaks, which are either purely magnetic in the case of red, or which have a mixture of magnetic and non-magnetic scattering. So these red ones are actually the important data points because they just contain purely magnetic Bragg peaks. And you can see that this doesn't fit at all. This doesn't fit very well, but this fits pretty well. So this is actually the correct structure for that compound. So it's called a C-type antiferromagnet with the spins along the C-axis. That's how you do the experiment.
Sorry, one question.
Yes.
Can you go with the slide?
Possibly. Hang on.
So for the various three models, it seems that the blue dots are more or less equally distributed for the three models. What makes really a difference between the three models? It's clear for the blue dots, the red dots where you have the magnetic properties. But for the blue one, can you simply say something, or you accept that the E is the best fit, and that's all?
So each of these dots is an intensity which has been measured and plotted on the vertical axis, and then the intensity has been calculated and plotted on the horizontal axis. So if it doesn't fit, for example, like this point here, it doesn't fit at all, that's because there's a contribution to that blue dot from the magnetic structure, which clearly doesn't agree. The calculation doesn't agree with the experiment. So ideally, you would want to have all these dots along this diagonal line here, and then that would be a perfect fit.
Yeah, but you have this scattered point on this range that are not on the line.
Like this one, you mean?
Yes, or also the cluster that you have there.
So that they're sort of clustered because the intensity of these peaks depends upon the structure factor. That means the interference of the scattering from the particular structure. That's why they're sort of clustered like this. I mean, this has got a rather large error bar, so probably this is just experimental error that it's not fitting.
Okay.
This is probably about as good as you can get for this type of method.
Thank you.
Right, so now knowing what the magnetic structure is from experiment, one can calculate using ab initio techniques the band structure. And you can see that we're using this model for the magnetic structure together with the known crystal structure. One can calculate the band structure, and you can see that the chemical potential, which is the zero level here, intersects the bands at this point, these points here, and these points here. And these are actually very close to these gapped Dirac cones, which were predicted earlier. So this one here is one of the Dirac cones, and this is the other one. The chemical potential is not actually at the nodal point, which is, it would be in these gaps here, but it's close. And what that means is that you would expect the conduction electrons to have some characteristic of the Dirac fermions, and indeed they do. So if you do, so I haven't got the data here, but if you do quantum oscillations measurements, you do see Berry phase effects in the quantum oscillations measurements. So that's why I was focusing on those 2 points. Now, another question that's interesting is what are the couplings which cause this magnetic structure to occur? So we think about magnetism as being due to exchange interactions between spins, and for these relatively localized moments, you expect there to be exchange interactions between nearest neighbors and maybe next nearest neighbors in this direction, and also along the C-axis to make the structure three-dimensional. So it's interesting to try to determine these experimentally, and the way to do that is to measure the magnetic excitation of the system. And magnetic excitations of an ordered magnet are just spin waves, just precession waves of the ordered moments. So you can do this by using inelastic neutron scattering. And because I'm an experimentalist, and I think we should be honest about these experiments, they're not very easy to do. And one of the problems with inelastic neutron scattering is that you need quite large masses of sample. So what you have to do is grow lots and lots of single crystals, which only grow, I think the dimension here is about 3 millimeters. This is about 3 by 3 or 3 by 4 millimeters. Relatively small masses, about 20 to 40 milligrams, something like that. That's not enough to do inelastic neutron scattering. So what you have to do is you have to have a good student who has a lot of patience and is very persistent and will co-align each of these crystals one by one in the same orientation and then glue them onto a plate like this. This is one side of the plate, and then this is the back side of the plate where there's another 9 or 10 crystals have been glued. So this then gives you about a gram or just under a gram's worth of sample, and that's enough to do inelastic neutron scattering experiments. And this is what inelastic neutron scattering data could look like. So what you're seeing here is you're seeing a scan where on this axis is the momentum of the neutron. This is in momentum space, and then this is the intensity. And so it's a series of these momentum scans for different excitation energies, going 5, 10, 20, 25, and so on in this direction. And you can see that at low energies, there's no signal. And then once you reach this energy here, you get a very, very strong spin wave scattering signal. And as you go to increasing energy, it gets broader and starts to split into two. And these two then disperse with energy outwards until eventually at around about this energy here, it becomes almost indistinguishable from the background. So this is essentially a measurement of a spin wave dispersion relation that starts from a point and then goes upwards like this. If you do this in different reciprocal space directions, then you can build up a whole three-dimensional map of the dispersion relation of the spin waves. And that's what we have here. So this is a plot showing the energy versus the momentum in different symmetry directions of the crystal. And you can see there's the white points, the experimental points, and the background color is a calculation just using linear spin wave theory from the simplest possible spin Hamiltonian that you can write down that would describe this sort of spin excitation spectrum. So it's just got some Heisenberg term here involving some nearest neighbor, actually just those three nearest neighbor couplings, J1, J2, and JC. And then it's got some anisotropy to make the spins point along the C-axis. And that's sufficient to give a reasonably good description of the experimental data. And from that dispersion relation, you can extract the numerical values of these exchange constants, J1, J2, JC, and the anisotropy constant. And I'm showing you this table because we've actually done this experiment not just for the compound I've been showing you, but also for some bismuth compounds as well. And it's quite interesting to compare each of these compounds. Most of them have the same space group. This one's slightly different, although the local environment is very similar. The antimony compound, because antimony is smaller than bismuth, the lattice parameter in plane is substantially less than the others, although the outer plane lattice constant is almost the same. And if you look at the nail temperature, this has a higher nail temperature, which is what you'd expect because the manganese atoms are closer together. And also has higher values for these two exchange. These are two in-plane. See, I think I've got a picture. Yeah. These are the two in-plane exchange interactions between the manganese within the AB plane. So they're bigger than for the bismuth compound. But what I'm highlighting here in this column is the coupling along the C-axis, which is the coupling between these manganese, which are quite a long way apart. And you can see that for the antimony compound, this is 5 times bigger than for the bismuth compounds. Why is it so much different? So we don't know the answer for sure, but one possibility is there may be different contributions to the coupling, magnetic coupling between these atoms that involve these intermediate orbitals. So there could be some sort of antiferromagnetic super exchange, which tends to cause antiparallel alignment of spins. And that could be competing with some kind of metallic exchange, which involves the electrons on these antimony orbitals, which is where the conduction band is largely located in real space. And it could be then that because antimony is smaller, the antimony orbitals are more tightly bound to the atoms. So the super exchange part of the exchange is probably suppressed, is probably lower. And the electronic sort of metallic part of the exchange may be the same strength as in the bismuth compound. And so, but that then, relatively speaking, that is the bigger exchange contribution. So we think that in the antimony compound, the effect of the topological electrons in this level here is probably more important than in the bismuth compounds. So it might be a good material for studying experimentally the effects of topology, the coupling between topology and magnetism. All right, so the message there was really to illustrate, the main thing was to illustrate how different magnetic structures have caused different electronic topologies. I now want to move on to another property of topological systems, which is that they have anomalous transport. In particular, they have an anomalous Hall effect, which is a contribution to the Hall effect that's not due to an external magnetic field. It's just intrinsic to the sample. And I want to show some example of this effect in this compound, manganese 3. Actually, I'll just show the germanium compound, but the same effect is observed in a number of different members of the same structural family. So in case there aren't any aficionados of Hall effect, the anomalous Hall effect is, well, the normal Hall effect you all know about is where you pass a current along a rectangular bar in some direction like this, and you apply a perpendicular magnetic field, and then what you measure is a voltage perpendicular to both the current and the magnetic field. So this is a standard Hall effect, and it's described by an equation here. Electric field in, say, the y direction is equal to some coefficient rho yx times the current in the x direction. And what that gives you typically in a metal or a semiconductor is a linear variation of this coefficient, this resistivity coefficient with magnetic field. The anomalous Hall effect is an additional component to the Hall effect, but which is, after a very low field region, is essentially constant with magnetic field. So it's a constant contribution, an additional contribution to the Hall effect over and above the conventional Hall effect. And actually it switches sign with magnetic field. So as you go through zero here, the anomalous part switches sign and then becomes constant again. And this effect has been known for a long time in ferromagnets. It appears in ferromagnets. But only very recently has it been observed in antiferromagnets, where you have no net magnetization in the system. And nowadays we think about we understand this anomalous Hall effect as being due to consequence of this special Berry phase, which occurs when you have these closed cycle orbits in topological materials. So that's how we understand the origin of this effect. And it's been measured in a number of antiferromagnets now. This was actually the first. Actually, manganese 3 tin was the first, but this isn't related. This plot here is showing data of this rho yx, is written slightly differently, but this is rho yx as a function of magnetic field at 2 temperatures here. And you can see that in this material, this is just the anomalous part, so the normal part has been subtracted off. So we just got the field independent part, which switches sign as you go through zero field. And what's nice about this material is that the anomalous Hall effect is present even at room temperature and above, and is actually switchable in a very, very small magnetic field. Just a few hundred oersteds is required to switch the sign of this anomalous Hall effect term. So you can see how this could be interesting from a practical point of view, perhaps as a magnetic field sensor, or a way of storing information in an antiferromagnet, which is not susceptible to the kind of demagnetization effect that you get in ferromagnetic storage materials. So it can have some practical application. This is the structure of manganese 3 germanium. It's actually got 6 manganese atoms in the unit cell. They're arranged in Kagame patterns, so in layers of corner sharing triangles. So there'll be another triangle over here in the next unit cell. And there's 2 of these Kagame layers per unit cell. And back sort of nearly 10 years ago, before the magnetic structure of this material was known, there was an attempt by Kubler and Felser in what's become a landmark paper actually, to calculate from first principles the magnitude of the anomalous Weyl effect for magnetic fields and currents in different directions. They actually calculated the conductivity rather than the resistivity, but it's measuring the same thing. So these are just for a current going in one direction, measuring a voltage in an orthogonal direction given by these 2 coordinates here. And because they didn't know what that true magnetic structure was, they just tried calculating for a number of examples of possible magnetic structures. It was known that because from its triangular pattern, it was known that the spins were at 120 degrees to one another, like you see here in this picture. But it wasn't known how the spins on the red sublattice were related to the spins on the blue sublattice. So you can see they just tried different patterns, including ones where the spins were actually tilted out of the horizontal plane. And you can see that it makes a huge difference. So for example, this magnetic structure has identically 0 anomalous Weyl effect. So no anomalous Weyl effect in any direction. Whereas this structure here has no magnetic Weyl effect for these directions of field and voltage, but has quite good anomalous Weyl effect for these 2 directions. And even the sign changes sometimes depending upon what magnetic structure you choose. So the point is that the exact details of the magnetic structure makes a huge difference to the observable properties. So it's important to know what the correct structure is. So it turns out that, so we did the experiment to measure what the correct structure is, and it's not actually very easy to do. Using for non-collinear magnetic structures like this, you have to use quite sophisticated polarized neutron diffraction techniques. So I don't go into the details, but it turns out that this is the correct structure, which is none of these at all. So somebody should, maybe they already have, but somebody should try calculating, rerunning the calculation, but for the correct magnetic structure. It'd be interesting to know whether it then comes out to be what's observed experimentally. So so the conclusion from that was that, again, that you actually need to know the very precise details of these structures if you want to calculate the correct transport properties. So finally, I wanted to illustrate these principles of coupling of magnetism and topology with some europium-based systems. Large family of europium compounds exists where you have divalent europium together with some other metal atoms. And divalent europium is quite nice because amongst the rare earths, usually you get a combination of orbital angular momentum and spin. But europium 2+ actually just is a pure spin, where all the 7 electrons, the spins of the 7 electrons just add up into a total spin of 7/2. So it's quite a simple system magnetically. You don't have to worry about orbital angular momentum. And the other thing is that because it's a rare earth, the F electrons are very tightly bound and they're very localized. So they don't really contribute towards the conductivity at all. So it actually acts as a kind of magnetic subsystem, which is then coupling to the conduction electrons and affecting the conduction electrons, but not actually participating in any electrical conduction itself. And we've been looking at a whole bunch of these europium compounds in the last 2 or 3 years. I'm just going to focus on this one, which was the first one we looked at. This is probably the one that has the most interesting properties and the easiest ones to explain. So I'm just going to tell you a little bit about this compound here, europium cadmium arsenic. This is the unit cell. It's actually hexagonal, which means that the europium atoms here form a triangular layer, triangular sublattice. And then in between, the arsenic and the cadmium also form triangular, so 2-dimensional lattices, but interleaved in this space here. And it was known for some time from bulk measurements, so magnetization versus temperature measurements, that there was an antiferromagnetic phase transition just below 10 Kelvin. And the question then is, oh, and it was also known from magnetization versus field that the saturation, it's possible to saturate, in other words, to fully polarize all the europium spins in relatively low fields of between 1 and 2 Tesla, depending upon which direction you apply the magnetic field. And the saturation value of the magnetization corresponds to the fully aligned 7 Bohr magnetons that you expect for a pure spin 7/2. So this is confirming that the moments on these europium spins are not participating in any kind of metallic process. They're just fully localized F moments. And I won't go into the details of how one does it, but so the technique of choice for measuring magnetic structure is neutron diffraction. But if those of you who've done any neutron diffraction will know, cadmium is actually a very absorbing material for neutrons. You actually use it to shield apparatus so that they don't get hit by neutrons. So it's a very absorbing material, and europium is actually even more absorbing than cadmium. So this compound is not a material that you would want to do neutron scattering from. It would be impossible to get any kind of signal out of it. However, you can use another technique, which is called resonant X-ray scattering, which is similar in principle. It's a diffraction technique, but this time you're using photons, and you tune the photons to one of the atomic absorption resonances, and you get strong enhancement from this in the diffraction. And by doing clever tricks with the photon polarization before and after the diffraction and fitting those to a model, you can determine what the magnetic structure is. And it turns out that this is what the structure is. It consists of layers of ferromagnetically aligned europium spins pointing horizontally, and then from one layer to the next, they just reverse direction. This is what we call an A-type antiferromagnet. This is the magnetic structure. And how does that then affect the band structure? So to know what the band structure is, you can measure it with angle resolved photoemission spectroscopy. This is an example of some data that we obtained at the Diamond Light Source in the UK. This fuzzy band here this is all the F electron bands, so unresolved. And then you can see some quite sharp bands here, which come from arsenic 4P and cadmium 6S, which will be up here a little bit. These are ab initio calculations done by Maia. What the comparison with the experiment shows is that, broadly speaking, the ab initio calculation is getting actually the details of these band structures rather well. So this gives us confidence that that you can calculate the electron bands in this material by this method. Rather you have confidence that it's giving you the right answers. And you can see that there's both in the experiment and in the calculation, there is a point here where there's something that looks a bit like a Dirac point, where bands come together at a node here. And of course, in the experiment, you can't measure the bands above the node, but calculations show that there are bands coming away, or dispersing away like this. And you can see there's a little gap here. So I just want to focus on the band structure a little bit more carefully. So this is the band structure that Maia calculated using the experimentally determined magnetic structure. And with this magnetic structure, if you look at it very carefully and you stare at the symmetry, you find that it has spatial inversion symmetry. It doesn't have time reversal symmetry, but it has a kind of time reversal symmetry where if you reverse the spins, if you reverse time and then you translate the spins through one unit cell, then the structure maps onto itself. And these combinations of symmetry mean that these bands are all doubly degenerate. However, because the threefold symmetry of the space group is broken by the ferromagnetic ordering in the layers, you actually get a gap here forming at the place where the bands come together. So there's a very small gap here. It's only about 50 milli-electron volts, but nevertheless there's a gap here. And that means that in principle, if the system had a chemical potential right at this point here, it would be some kind of semiconductor. Now, interestingly, Maia calculated another case, which is what happens if you apply the magnetic field along the z-axis. And in that case, you recover the threefold symmetry of the crystal structure. And that means that this point here the crossing of these two bands is protected by that symmetry. And so this point here is actually a Weyl point. And in this particular situation where you have ferromagnetically polarized spins, you break time reversal symmetry. So all these bands are now singly degenerate. And that's why it's a Weyl point here rather than a Dirac point. So we've actually been able to use a magnetic field to convert from something which is essentially a kind of semiconductor. It's actually a topological semiconductor or a topological insulator, this phase here. So we've been able to convert from that into a Weyl semimetal just by applying 1 or 2 teslas of magnetic field. And this is what's exciting about these materials, these topological materials which contain magnetism, is that you can potentially use magnetic fields to change the band topology and to do radical things to observable properties in principle. Just to focus on this point here, this is the important point where the chemical potential is a little bit more closely. This is now expanding very much the energy scale here. So we're just looking at a window of about 60 millielectron volts. And this is the antiferromagnetic case where you have this gap of about 50 millielectron volts around a chemical potential. And this is the case where you have the ferromagnetically aligned spins and you have these protected Weyl nodes here. And you have exactly 2 of these Weyl nodes. And that's interesting because in topology, there's a number of predictions that have been made for systems with just a single pair of Weyl nodes at the same energy. This is a very kind of, it's a very important model system which people, theoreticians have been able to calculate what are known as semi-universal properties of such a simple system. But there are actually no experimental systems which have been found to have this kind of clean structure with just a single pair of Weyl nodes at the Fermi level and no other trivial bands complicating the system. So this is potentially an example of the ideal, the best possible, simplest possible Weyl semimetal that you can get. Another way of looking at this Fermi surface where you have the ferromagnetically aligned spins. Now in 3 dimensions, the Fermi surface would simply consist of 2 points where the Weyl nodes come together, where the bands come together at a single Weyl node. So you just get two points here and here along the Z direction in the unit cell. So this is the sum total of the Fermi surface in the ideal case. Now, there's a but, and the but is that we did quantum oscillation measurements on our crystals. We actually found that we measured oscillations on these crystals. And when you measure quantum oscillations, what you're measuring is the Fermi surface. And from the periodicity of these oscillations, plotted inversely versus the oscillation number, so-called Landau level index, they fall on a straight line. And from the gradient of that straight line, you can calculate the area of the Fermi surface perpendicular to the magnetic field. And this is the number you get. It's very small. It's about 0.1% of the area of the Brillouin zone. So going back to this picture here, the area of the Fermi surface, you can think of it as being like the projection of this, like a little circular projection perpendicular to the C-axis. It's about 0.1% of the area of this hexagon here. So it's very, very small, but it's not 0. And what that means is that in the real sample, it's slightly doped. So there's some conduction electrons. It's not, the chemical potential is not exactly well known. And we calculated from the electronic dispersion above and below the Weyl node that the chemical potential is actually about 50 millielectron volts below the top of the valence band, about 50 millivolts below the Weyl point. We also measurements of the anomalous Hall effect, and as I mentioned before, in this simple case where you just have a pair of Weyl nodes, there's a theoretical prediction from some years ago now that this anomalous Hall of conductivity should have what's known as a semi-universal form. In other words, it just depends upon a bunch of fundamental constants, including E squared over H, which is the quantum Hall conductance quanta, multiplied by the separation of the Weyl nodes in K space. So in principle, one should be able to measure and verify this prediction if you had a perfect system with chemical potential exactly at the Weyl nodes, and you knew how far apart these nodes are. Now, we have a pretty good idea how far apart these nodes are, so we know what delta K is from Maia's calculations. But if you put the numbers into this formula, you get a value of 30 in these units per ohm per centimeter. Do the measurement, which we have done, we get an anomalous Hall value, which is at these, the red curve here is the anomalous Hall measurement, only 0.5. So we are quite a long way off the predicted semi-universal Hall value. And we think that probably the reason why this is because the chemical potential is this 50 millivolts below the var nodes. That means that you're getting contributions to the anomalous Hall effect, which are not just the ones responsible for this semi-universal form here. This form here is coming from surface states, whereas we've got conduction in the bulk as well. Nevertheless, this kind of motivates us and others to try to do experiments, to try to modify the experiments, to try to achieve a system where the chemical potential is exactly at the var node, and then it should be possible to confirm this prediction. So I'm going to conclude now and just thank and list all the collaborators, especially some of the graduate students. Jean-Marie So was involved in all this work, and Siobhan Tobin, who co-lined those crystals and participated in that experiment, and Marijn Run, who did some of the X-ray scattering experiments, and all the people at the sources, the facilities, and Amalia Caldia in our lab was responsible for magnetotransport, and Ms. Schroeter led the ALPES data. And Fernando Juan and Maia were our great collaborators on the theoretical side of the work. And we got crystals from my colleague in Oxford, Prabhakaran, and groups in Shanghai and Beijing. Right, I just concluded a few messages. The main message I want to convey here is simply to illustrate how magnetic order and magnetic fields can be used to control electronic band topologies. And I've given you some examples from manganese and europium compounds. There's many other examples in the literature, but these are just the ones that we've been working on. The details of the magnetic structure really matter. You have to know whether the spins are, collinear or non-collinear, what the propagation vector is. All these things have to be determined experimentally, because it's actually very difficult to calculate these kind of details from first principles. The energy difference between these structures is very small. And so I haven't really said much about the experimental techniques, but modern neutron and synchrotron radiation scattering techniques have evolved a lot in the last few years, and it's now possible to really measure very tiny crystals and to measure very sophisticated and complex structures with these techniques now. And so there's some literature in case anybody's interested. So thank you very much for listening.
Yeah. It seems that you consider that the magnetic structure and the atomic one are decoupled somehow, but there could be some coupling.
You mean that it might cause a distortion of some sort? Yeah. Well, that's true. One does, of course, see magnetoelastic coupling. So I suppose the question is, which is partly for the ab initio, is to what extent a tiny shift or structural distortion could affect the electronic structure. I mean, we don't see any evidence for any distortion in the experiment in these compounds, particularly the F electron compounds. Because there's no orbital angular momentum, the coupling will be quite weak, I think. So it's a good point. This is something that one should always be aware of and be careful of. We haven't seen any evidence in these particular compounds, but yeah, good point.
More questions? Okay.
So I've seen, I think, in the case of the European compounds, that you have stated that they are not strongly interacting compounds, but then in the calculation there was a hard improvement. So which is the way of, what's the reason behind that?
So in the European compounds, they are ordered magnetically, so they are correlated in that sense. There is coupling between the europium atoms, the europium spins, which causes them to order magnetically at about 10 Kelvin. And then those those F electrons couple to the conduction electrons through some kind of exchange mechanism and cause the electronic bands to split and move around. And that's what generates the Weyl nodes. But the conduction electrons themselves are actually rather uncorrelated. There's very few correlations between the conduction electrons. You can think of those as as single electrons, non-interacting electrons, and that's why the ab initio calculation works so well, because there's almost no correlations between the conduction electrons. So I think we have two subsystems here. We have the conduction electrons, which are basically non-interacting electrons, and we have the F electrons, which are weakly coupled together. And then these systems are coupled together through some exchange. The manganese compounds are much more correlated. So the manganese d orbitals are actually partially conducting. They're represented in the Fermi surface. So those are much more conducting, and I think it's much more difficult then to calculate band structures and meaningfully for those materials. In fact, if you look at the ARPES measurements, they're on manganese tree germanium. This is the one I showed with the large anomalous Wall effect. The measurement shows very, very indistinct bands, very, very broad bands, and this is telling you that the manganese orbitals are very correlated. So it's a good point. The degree of correlation is a good point, something one has to bear in mind.
Okay.
I have a question actually from Miguel Angel that is watching from YouTube. So does the space group symmetry constrain the possible arrangement of moments to determine the magnetic structure?
So you're asking about
basically, I guess that if you have some atomic positions with a given space group symmetry, I guess that he's asking that whether this constrains the possible arrangement of the magnetic moment.
Oh, I see.
In the of the structures that you are considering as possible ground states.
So I'm not sure whether this is his question, but one of the tricks for solving magnetic structures is to look at the possible symmetry allowed magnetic structures, assuming that when the system goes from the paramagnetic phase to the ordered phase, assuming that it's a continuous phase transition, and therefore one can then conclude that the magnetic structure should be a single irreducible representation of the paramagnetic space group. So if you make that assumption, then you just get a small number, usually 3 or 4, or not many possible structures to look at. And then what you can do is you can compare each one of those possible symmetry allowed structures with the experiment. So in practice, that's how it's done. You don't assume like an infinite number of possible magnetic structures and try and compare them with the experiment. You constrain it using symmetry. So that's what we did with actually all these materials I've shown today. We use that method to analyze the data and find a magnetic structure.
Thanks. Yeah.
Yeah, thank you. Thank you for the question. Good one.
Any more questions? Can you ask on Zoom if anyone has more questions?
Concerning manganese compound, you had this C-type, 2 C-type structures, so they differ only the direction of spins.
One's like this and one's like this, yes.
Ah, okay.
So I think one of them was like this with the spins ferromagnetically but pointing in the plane, and the other one was like this with them pointing.
Yeah, so it's just, I mean that, was it, so the direction of the spin is determined by anisotropy, magnetic anisotropy. So this is just a relativistic effect. So you have to calculate relativistic calculations, relativistic bands.
You would have to calculate relativistic bands. I think the difference between, so the anisotropy is very small. It's just in the order of 1 millivolt, 1 millielectron volt. So this is kind of the resolution limit of ab initio calculations. But yes, it comes from spin orbit coupling, very, very weak spin orbit coupling effects, relativistic effects, as you say. Yeah. So I mean, it's not really relevant, I think, for the band topology, because that's on a higher energy scale. But it's important for determining which direction the spins are pointing.
Could you do any RPS measurements on manganese antimony compounds, like to complement your preferred?
Yes, so so I didn't show them, but so we haven't done those measurements, but other groups have done those measurements, and so they exist in literature.
And
And
they match your calculations of the magnetic.
well, actually, that's a good point. I'd have to check whether they've actually been done for the correct magnetic structure. So often these calculations are done for an assumed magnetic structure. And then, of course, as I've tried to show today, that doesn't always give you the right answer. So yeah, so I need to see whether the literature has any calculations for the correct magnetic structure, but that's, yeah, that should be done. And the ARPES, yeah, the ARPES has been measured, but I don't know about the calculation.
So I see there were a lot of results from experiments and ab initio calculations.
Yeah.
Is there also any model that's more general and can be applied to different materials to understand this physics? For example, from a Kondo point of view, or because all of these calculations are quite material specific, and I was wondering whether you can make a more general model that can be applied to several.
Well, you can make a toy model for certain band features, like you can make a model for a pair of Weyl nodes, and for example, by mapping them onto a tight binding model or something like this, just to make some kind of simplified model with just a small number of basis states, and then you can then calculate properties from that. But actually, we found that the ab initio is very, very useful as a way of giving us an idea about what features might exist. I think maybe for a very detailed understanding, well, you can extract the wave functions from ab initio, so you can get most of what you need to understand what's going on from ab initio. That's what I think, that's the way the field is going at the moment.
It does help that, like, for similar materials, results are also very similar. But now we focus on one.
Well, okay, so we were talking about this morning, actually. So there isn't a way at the moment of being able to just say, looking at a crystal structure and saying, okay, this has got Weyl nodes. This will be the size of the anomalous Hall effect. There's not really a simple understanding of what contributes, what dominates there aren't any kind of organizing principles for calculating anomalous Hall effect or other magnetotransport effects. So I think we're thinking about how we can extract what is the essential physics that tells you how big an anomalous Hall effect would be, and for that, probably some simple models might be a good way to go.
Thank you.
Okay, are there more questions? If not, well, we'll thank Andrea again.
Thank you.
His office is in this corridor on the right. If anyone wants to talk to him, he's gonna be there this afternoon.